Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to everyone. So today, I'm Haslinda Muhammad Sidek from University Malaysia Sabah. I would like to present my research work entitled of Water Absorbent Material Derived from Self-Assembled of Metal Organic Framework and Metal Oxide Nanosheets. So here is the contents of my presentations. Before that, let me give a brief introduction of my research background. Okay, so for my research, I focus on investigation of the water adsorbent materials. So this water adsorbent is actually an important material that has been used in the electric dehumidifiers. Nowadays, the commercially available adsorbent that has been used in these dehumidifiers comes from the porous materials such as silica gel and also zeolite. However, this adsorbent material still needs more improvement in order to enhance the water absorptivity. To produce a good water absorbent materials, that materials need to fulfill these requirements. The first one is the low relative pressure and steep water uptake. The second one is the adsorbent material must possess the high water uptake capacity. And the third one is, of course, the water stability. The material must be stable enough. And lastly, it must have a low regeneration temperature. Okay, one of the materials that has gained a lot of interest from researchers is metal organic frameworks. So this MOF has its own unique properties such as high surface area and tunable pore structures. These unique properties of MOF can lead to the improvement of its absorption capacity. So it is proven because of this material has been widely used in various kinds of applications, such as the gas absorptions, gas separators, sensors, and also catalysts. However, even though it is an excellent material, especially for the absorption application, it's still inadequate to meet all the requirements for the water absorbent that I have mentioned in the previous slides, especially for the energy efficient water cooling system. Okay, for me, it is such a waste if we leave behind a really good materials like MOF, even though it has a lab performance, especially in water absorptivity, but still there's another way for us to do in order to improve their performance. So what I did in my research was I used another really good materials, which is nanosheets. So this nanosheets has thin thickness that can provide very large surface area, so it can serve as an effective substrate for MOF growth. So just imagine that we have a piece of paper and we know that this piece of paper is very, very thin. So this piece of paper can serve as a platform to grow the MOF nanoparticles on their surface. Okay, it is similar to this situation in which I use the nanosheets as a platform to grow all the MOF nanoparticles on the surface of nanosheets. So this is what we call as hybridization. Okay, next we move to experimental procedure. Okay, in my work, I use the zirconium formary MOF and also the IO2 nanosheets. So I use zeta potential in order to measure the surface charge of these two materials. As you can see from here, the MOF has the positively charged, while the IO2 nanosheets has a negatively charged. So what I did was these two materials can be easily mixed together because of the opposite surface charge. So this is what we call as a self-assemble method. And after the mix together, it can form the fluctuations. So we can see a precipitate from here, and this precipitate, we call it as a nanohybrid. So in order to study the effect of the TiO2 nanosheets on the performance of these materials, I use different content of the TiO2 nanosheets from 1 weight percent up to 7.5 weight percent. Okay, now let's move to the next session, which is results and discussion. Okay, so I test all the prepared samples with powder SRD. As you can see from here, the ZT here is meaning that the nanohybrid sample. So Z here represents the zirconium fumarate, T is for TiO2 nanosheets, and the different number here corresponding to the different weight percent of the TiO2 nanosheets. As we can see from this powder SRD pattern, all of the ZT nanohybrid shows the similar bright reflection to that of the zirconium MOF. So we can say that the ZT nanohybrid has been successfully synthesized. And then I characterize all the samples with FTIR spectrum. Okay, as you can see from here, there is a PVP. The PVP here, I forgot to mention in the previous preparation method. I use PVP as an additive or the stabilizing agent in order to produce a nanoparticles. Even though there is an addition of PVP, but we can see that there is no detection of PVP at all in the samples of nanohybrid. But the ZT nanohybrid shows the similar IR spectra to those of the pristine zirconium fumarate. And then, in order to prove the successful incorporation of TiO2 nanosheets in the nanohybrid, I characterize the sample with the same spectrum. So actually the TiO2 has a lot of bases such as anatase, rutile, and also protonated. Protonated TiO2 here belongs to the TiO2 nanosheets. And we can prove that the incorporation of the TiO2 is successfully done in this nanohybrid because we can see the ZT nanohybrid here shows the similar spectra with that of the protonated TiO2. Okay, for the morphological study, we can see that here the TiO2 nanosheet is successfully prepared and it shows a very thin two-dimensional sheet-like structure. And meanwhile, for the pristine zirconium fumarate MOF, it shows the spherical particle with the size of 50 nanometers. And the successful hybridization between the TiO2 nanosheets and the MOF can be shown in this DEM image, in which we can see that the nanoparticles of MF is uniformly distributed on the surface of the TiO2 nanosheets. And from EDS study, we can also confirm the existence of the uniform distributions of all elements in the entire nanohybrids. Okay, now let's move on the water absorptivity of the prepared samples. So this black line here represents the pristine MOF, while for the red and blue lines represent the ZT nanohybrids. So firstly, let's take a look on these black lines, which is the pristine MOF. As we can see from here, this MOF shows the common water isotherms as similar to the previously reported. So we can see that there's a gradually increase from the low relative pressure up to pressure of 0.6. Okay, and the maximum water uptake for this pristine MOF is about 40%. However, upon hybridization, we can see that the water uptake for the ZT nanohybrids is reduced, especially at high relative pressure. But what I want to focus here, what I want to highlight here is the enhancement of the water uptake at a very low relative pressure, which is below 0.1. So you can see here, even though it's not that significant, but still we can see there is an improvement of the water uptake upon the hybridization. We can see that is in these highlighted sections. There is a little bit of enhancement of water uptake, which is at a very low relative pressure. So we need high water uptake at a low relative pressure because it is convenient for the application. Okay, so what is actually happened here? the enhancement of water uptake at a low relative pressure might be due to the enhancement of porosity upon hybridization, meaning that after we hybridize the MOF with the TiO2 nanosheet, the porosity of that material is improved. When the porosity of the material is improved, the water affinity is also improved. That's why we can see the enhancement of the water uptake of the nanohybrids. Okay, here comes the conclusion of this presentation. Okay, we can conclude that the water absorbent materials were successfully prepared by really simple method, which is self-assemble method. And this the enhancement of water uptake, especially at a lower relative pressure, is mainly caused by the improvement of the water affinity with the greater porosity upon hybridization between MOF and also TiO2 nanosheets. Okay, with that, I end my presentations. So thank you to everyone and have a good day.